Okay, so we're going to look at three different types of Poisson distribution questions here. Now, obviously, it's going to be quite obvious that they're Poisson questions because that's what I've said, but we're still going to go through proving why they're Poisson each time. Right, let's have a look at the first question. Okay, so we've got a publishing company that hires a proofreader to check their novels. The proofreader finds that there is, on average, 3.8 errors per page. What's the probability that there are 5 or more errors on the next page? Okay, we've only been given a little bit of information, right? We know that we can use Poisson here for a couple of reasons. First of all, you can't have a double error, right? A word's either right or it's wrong. So there can't be 2 errors at once. All right, so can't happen simultaneously. Check. All right, we're talking about something that's continuous, and it's not entirely continuous, but it's close to continuous. In a page of text, there is maybe 500 or 600 words and 3.8 errors. It means that there's not enough that the probability is going to change once you add 1 or 2 errors. It's not going to be an issue. Okay, we also have the probability is proportional to the range. Probability is proportional to the range because it's given us an average per page. We'd expect that on 10 pages there'd be 38 errors. There's no reason to say that as that change that's likely to change. Now, if we cut it down really, really small, maybe not, but that's when we got down to a number of words. But overall, that's likely to happen. Okay, the next one is independent. Finding one error doesn't make it more or less likely to find another one. Now, this one here is probably true, but it could be that they're more likely to find errors at the times when the author was tired. So that one is a probably. Right. And generally the independent one is a probably. You can never know for sure that something is totally independent, or it's very unlikely to be able to know for sure that. Okay, so we've got 3.8 errors per page. So that's our lambda. Our lambda is 3.8. Okay. Sorry, draw my lambda back to front. Lambda is 3.8. And so now we want the probability that there are 5 or more errors on the next page. Now, to find that, what we're going to do is we're going to find the probability that x is less than or equal to 4, right? Because the probability that x is greater than or equal to 5 equals 1 minus the probability x is less than or equal to 4. Now, the beauty of this is we just bang it in our calculators. We put our lambda or our mean, whichever one, depending on what calculator we've got, and then we find the probability that x is less than or equal to 4. And basically we bang that in the calculator, and that equals 0.6678. And once we know that, that means that the probability that x is greater than or equal to 5 is equal to 1 minus that, so 0.3322. And that is how we do that question. Okay, now I couldn't resist throwing a cricket question in here. Kyle Mills, well, that should say took a wicket in 80.4% of matches that he played in. Estimate how many wickets he took in his last 100 matches, explaining your reasoning and any assumptions that you made in the process of coming to your answer. Okay, so again we look at our 4 conditions for Poisson and see, is this one of those situations? Well, obviously it is because it's in this section, but let's have a look at it. First of all, is taking a wicket or not independent? Well, probably not, but it's we could assume that it's close enough, right? Again, whenever we're looking at independence, it's almost always a probably or a possibly, right? Proportional. If we went to 2 or 3 matches, we'd expect that the number of wickets to roughly reflect that. Probably. Right. The next thing that we want to know is if we got a continuous. Well, in a cricket match, you bowl 60 deliveries, so it's not strictly continuous, but close enough. All right, and can we have simultaneous? That's right, we can't have simultaneous wickets. You either get a wicket or you don't. There's no 2 or 3. You don't score doubles. All right. So what we know is that he took a wicket in 80.4% of matches. So we know that probability that x is greater than or equal to 1 equals 0.804, where x is the number of wickets. Right, that's what we know. And we use that to therefore figure out what probability that x equals 0 is. Because if he took one in 80.4%, that means there's 19.6% that he didn't take it. 0.196. Now, if we've got Poisson, which we've just established that we have, then what we want to look for is we want to use our inverse Poisson rule, which is that lambda equals negative log of the probability that x equals 0. So our lambda is equal to negative log of x equals 0 of 0.196. So lambda equals 1.629 or 1.63. Right. Which means that overall we'd expect, so that's our lambda for one game. Lambda for 100. Well, because it's proportional, we just expect to be 100 times that, 163. We'd expect them to take 163 wickets. Okay, the number of goals in German football matches last season averaged 3.6 per match with a standard deviation of 1.9. What's the probability the game had 0 or 1 goals? Explain how you got your answer, including any assumptions that you made. Okay, so the interesting thing here is that it starts out reading like a normal distribution question because it gives you a mean and a standard deviation. But the problem is when we look at this, that with that mean and standard deviation, if we go 2 standard deviations away from the mean, we're going to be in negatives. So we obviously can't use normal here. Also, a number of goals is a discrete thing. You can't get 1.2 goals. And so we think about, well, what are some of the things that would lead us to think that it's not normal distribution? And the fact that it's not normal distribution is that the mean minus 2 standard deviations is less than 0, but 0 is, not 0, negative answers is not possible. So it's not normal. So the next thing that we think about is, well, what could it be? Well, goals are something that are, you can't get it, in football you can't get a two-pointer. You only get one or other, so it's not simultaneous. Right. The longer the game goes, the more goals you expect, right? So proportional. The vaguely independent, again, we could say they're probably independent. We can't be 100% sure they're independent, because obviously in games between teams that have got a good attack and a good defence, we'd expect more goals, and in game, against a bad defence, in games where we've got the two defensive teams, we'd expect less goals. So it wouldn't be perfectly independent. When one goal happens, it'd be more likely to have others, but it turns out that it is actually reasonably independent. It does fit to a Poisson distribution pretty well. And we've got a continuous range. Minutes. Okay, so given that, the next thing that we have to check, if Poisson then standard deviation would be the square root of lambda. So we look at what's the square root. So we want to find the square root of 3.6 and see, is that close to 1.9? Right, it probably won't be exact, because it doesn't tend to be exactly that, but the square root of that is 1.897. Is that close to 1.8? 1.9? Well, yeah, it's really close to 1.9. So, so we can assume Poisson. Alright, now the question was, what's the probability a game had 0 or 1 goals with a mean of 3.6? So, at that point here it becomes a pretty simple question. The probability x is less than or equal to 1, and then we just bang that in our calculator using the NCD function because it's cumulative. Okay, 3.6 is our lambda, our x is 1, less than or equal to, and it comes out to 0.126 is the three significant figures. Right, and so we answer the probability of 1 or less goals 0.126. Anyone that's watched any German football knows that there is actually a lot of goals, and there's a pretty low probability, about 12, maybe 1 in 8 that end up with 0 or 1 goals. Alright, so that is the final question. I hope that's been helpful.